You just saved maybe like 50 other students. Thank you, Sarah. All right. Yeah, so it doesn't seem like there are any questions. So let's move on to the second half of the questions. So converting. So my bad. You know, just because there isn't so conversions. Just because there isn't enough time to do everything, but yeah, so definitely, you know, like NFA to DFA conversion, that one's very important, and also the regular expression and the FA conversion, those are important, and also the ones about regular grammars and FAs. So yeah, so those are also important. I'm not covering them just for the sake of time. But yeah, definitely don't think the review material for this sort of session isn't completely exhaustive. There are a lot of things that I don't cover. So don't just think that just because it's not on here, it's not the final. There's a lot of things on the final that aren't on here. So for instance, stuff like this, right? So it's comprehensive. It's you know, it's everything you've seen in lecture. Okay. Yeah, but these, I mean, these are very, once you look at one or two questions, and like you probably saw in the midterm and the quizzes, they're pretty mechanical. If you once you get a hang of them, right? So, but I'd be happy if, like, you know, at the end, if anyone has specific questions about any of these, then I'd be happy to discuss them. All right. Yeah. So good point. Okay. So the second part of, you know, if you remember, the second part of the course started with context-free. So remember, you essentially finished off pumping lemma, and essentially, what is just a reminder, and I'm sure you've seen this circle probably 10 times by now, but what does the pumping lemma tell us? Well, if this is the set of regular languages, you know, you have you have an infinite number of languages in here, right? But what the pumping lemma for regular languages tells us is that there are some other languages that are not regular and that in fact sit outside of this bubble and that are here. Okay, and the next strata that you see in the course is for context-free languages, right? So that's a slightly larger, if you want to think of it, sort of informally, slightly larger set of languages, because all regular languages are context-free, but there are context-free languages which are not regular, right? So A and BN is here, the set of palindromes is here, and, you know, a bunch of others. So, you know, something like A, N, B, N plus 5, let's say, something like that. That's definitely not regular, but that's in the context-free languages. So stuff like that, right? So the first question here, which I'll let you do just after I read it, is, you know, given a language here, which if you could, you could show, if you wanted to, you could show was not regular, just because you have this kind of A and B N structure. You want to find a context-free grammar that generates the language here. So this is not that hard of a question. So try to take a minute to do it, and we'll look at it, and then I'll comment a bit about things regarding context-free languages. All right, so hopefully you had time to look at it a bit. So what's the, hopefully everyone knows this kind of trick. If you have, for instance here, you have a union of what sort of clearly are two distinct context-free languages, then you can use this trick where, you start your grammar G and you have your start variable S. And what your start variable S is going to do is going to let you go to two different types of derivations. So it's going to go to either S1 or S2. And S1 is going to be for here, and S2 is going to be for here. So what is S1? What should S1 do? Well, we know that we have this AN, BN structure. The only thing that is really necessary here is to that AN, BN structure, we want to add an extra KBs, and I know that K has to be at least 1. So remember, this is kind of a trick for, or kind of just a trick, a technique that you learn for creating context-free grammars is you set up the kind of AN, BN generation. So you set up your AN, BN generation. And then once you've done that, then you want to, so imagine you generate a bunch of AN, BNs. Once you finish that, then you want to move on to the extra BK, right? And so to do that, you can move on to the extra BK by saying, okay, I absolutely want to do I absolutely want a B, right? Because K has to be at least 1, okay? And then I'm going to go to variable A, right? Now variable A is just going to give me an extra amount of B's. So it's going to give me any extra amount of B's I want. And once I finish giving myself those extra B's using this transition, then I can stop using lambda, okay? And the same thing is pretty much going to happen for S2. For S2, I'm going to again use the same structure. I'm going to create my AN, BN sort of so I'll answer that question in a second. You can do S2 is AS2B, and then again using the kind of same principle, just add 4 A's because you want K to be at least 4, and then go to B, and then B is going to give you any extra number of B's. Oh, I see what you mean. Okay. So that is one valid grammar. But yeah, I think I just realized what. Yeah. AS1B. Wait, just give me a second. So you're saying S1A, S1B. I'm just trying to see if I can trick you. No, it seems like this is bulletproof. Yeah, because if you start with AS1B, you create a bunch of ANVNs, then you go here, you create a bunch of Bs, and let's say you go back, then yeah, that's fine. Yeah. So the thing to note was that you couldn't do BS1, because if you did BS1, then you could get a mismatch, right? You could get stuck with something like A B and then B A B, something like that. So that would definitely not be good. But yeah, so excellent point. You can also do this, and that's much cleaner. It uses less variables, which is nice. I just find this system to be more sort of explicit, but yeah, that's fine. So I feel like this is pretty standard. So I don't know if there are any questions about this, but that is a good point. Yes. So if there are no questions about that, I just want to, what did I want to say about CFGs? Yeah, so these tricks, so this is kind of like a trick using kind of S1B, You could have done the same thing with S2 if you had done S2 B, 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 right? So using this kind of trick to know how to get that extra K, that's an important trick. And then what's the other nice one, if you have something like A, N, B, K, where N is strictly, sorry, is different from K, then remember you can split this into two. You can say either N is strictly less than K or N is strictly greater than K. So that's another important trick to use if you're given that. I mean, usually what will happen, right, is you'll be given the grammar, and then you'll be given a question like, how many strings of length 5 are there, or what strings are generated by this language, or is it regular, is it context-free? You know, standard questions that you've seen already in the quiz are going to come up again here. Yeah, so that's what I wanted to say about that. Yes, okay. So I don't, yeah, okay, so there doesn't seem to be questions about this, which is good because this is fairly straightforward. So yeah, so we had seen about context-free languages. The other type of question I wanted to look at was a kind of trickier, true or false. So take a minute to think about this one, and we'll discuss it in a minute. All right, so hopefully you had some time to think about it. It looks like someone has already been able to answer it. So what is it saying? It's saying, you know, it's a true or false. And it's stating that the language here, let's call this L, this language is not context-free. So answering true would mean that L is not context-free, and answering false would be that L is context-free, right? And so if there wasn't this, right? Imagine for a second that this wasn't there, and I had said this, right? Then this is definitely not context-free, right? Because a possible string to pump so I'm going all the way to the pumping lemma for context-free languages for this exercise. But an example that you could pick would be something like, because we've shown that W, right, this over AB star, this isn't context-free. So what you could do is you could use the same, you could use exactly the same string for pumping up or down. You could use AM, BM, AM, BM. So what's happening here is you're just utilizing this portion, and essentially you're just setting W to lambda, okay? So this would be a way to show that this, if this isn't here, right, if this isn't here, it would be a way of showing that this is not context-free. But things change, so things change if I add this this thing. So this is supposed to kind of help you out a bit, because what it's saying is it's saying W in AB star and for some V over AB. So what does for some V over AB means? It means that you're allowed to pick which V it is. It means you're not saying for every V over AB, you're saying for, you know, maybe one V that someone picked at a point in time, okay? And so what that does is that makes my life a lot easier, because then I can just say, oh, well, okay, that means I can pick the V. So I can just pick V is lambda, okay? So then what this reduces to, it reduces to WR for W in AB star. And then we all know, hopefully we all know, that this is context free, okay? So true or false, this is not context free, is in fact, this is false, okay? No, so V does not contain lambda. V, you set V equal to lambda. No, so V is over, yeah, so maybe this wasn't worded correctly. Imagine this was V, for some V in AB star. Okay, so no, so I meant, because when you say a string over an alphabet, so if you say the string over the alphabet AB, right, the string over the alphabet AB, it's any string that can be created using the alphabet AB. Okay, so that's what I meant by that statement. So if you do see that in a test, then don't freak out, that's what that means. But it can also be converted, so that statement can also be converted to V is in AB star. Okay, and it's for some, meaning that you can pick the V that you want, which makes your life a lot easier, right? Because if you set this to lambda, then you can show that it is context free. All right. Yeah, so so the main takeaway from here, the idea was sort of the set notation. The set notation and the way that it's written is key. So if you have something like this where it says for some, then you have to give yourself the idea, then that means that, oh, I can actually pick something that helps me out, okay? So I hope that's clear. If it's not, you can stop me. But if it is, we can move on. So we can move on to the next, okay? We can move on to the, oh, can you re-explain? Yes, okay. Yes. So, okay, first of all, the language is context free. So this is false, meaning that, you know, it's the negation of not. So L is context free. So that's the conclusion. And so the reason why it is context free is because it says you have this, W is over AB star, for some V over AB star. The for some allows you to set V to something. It allows you to pick what V is going to be here, right? It's no longer a for all. It's no longer for all V in AB star. It's for some particular V over AB star that you pick. For some particular.
That's a pretty tricky question.
That is a pretty tricky question, so that's why I put it.
That's a good one.
Thank you. All right. So yeah, so that's why if you have for some particular V over AB star, then you're allowed to pick the V that goes in here, right? And so if you're allowed to do that, you can set V to lambda. If you set V to lambda, then this gives you the language of palindromes. You could have picked anything else. You could have picked V is, you could have set V to ABB. That would have still been context free. It would have just been, you know, less clean to explain why, right? But because it's for some rather than for all, then it allows you to pick the V and conclude that there is a setting of V such that this is context free. So that's why it's false. It's false because it is context free, so it negates this. All right.
I'm having trouble understanding why this is not the proof for all V is not context free. Like, let's say it said for all V,
Yeah.
and then you show that there is one. Wouldn't that be the contradiction that shows this is false?
No, that's a good question, but yeah, so it wouldn't lead to a contradiction, because the fact that you found the fact that you found one V doesn't mean that it's context free for all of the other V's that you didn't select, right? So if this was L is WV, whoops, WVVRW, and it was VW in AB star, then this is saying for any possible setting of V and W, all of these possible strings, right? But this is very different from for some V, because for some V, you're allowed to pick which V you want. In this one, this is any of the possible V's you can have, right? So it's any of the possible V's that can be created over the alphabet AB, okay? So because you can find one particular setting of V such that this is context free, then that leads to L being context free, okay? So I don't know if that, I hope that's clear. If it's not, let me know.
I got a question.
Yes.
What makes this language context free then? No, not context free.
So this language is not context free. Whoops, this should be R. This language is not, this language that I'm pointing out is not context free. But the one in the question is context free. Yes?
But why and how?
Why and so the question is why and how is this context free? So what is the specific question?
Yeah, but what make it context free then? No context free then.
Well, oh, okay. Why is this not context free?
Yes.
Okay, this is not context free because, for example, I can pick AM, BM, AM, BM in the proof for the pumping lemma.
Okay.
And then if you use the same argument for the language WW,
Mm-hmm.
you use the same cases, you're going to, whenever you pump up or down, you're going to get a contradiction. And so that's going to show you that L is not context free.
Okay.
Yes, Simon?
That makes sense. Thank you.
Okay, no problem. All right. Okay, so now there's a bunch of questions in the chat. Okay, so the answer is, okay. So the answer is it's false. Okay, so I worded it trickily on purpose because, you know, it's fairly possible that some questions like this can be asked. The reason why it's false is because, so let me get rid of this. Remember, let's read the statement carefully. The statement is true or false. This language is not context free, but I've shown that L is context free. So that means that the statement is false, okay? Because it is context free, okay? So that's why the answer is false. Okay, so let me just try to keep up with all the questions. All right, so there was a question about existence proof. Isn't it an existential proof that if we find some V, no, so it's not quite an existential, well, existence proof, I hope you mean. Existential proof is, you know, like existential crisis. But it's not an existence proof because you're setting it, you're not trying to find if it exists. You know it exists, and what you're doing is you're setting it to something that you know exists. That's the kind of, it's, I mean, it's not really a proof. It's just how you can use the statement to claim, to prove the claim, basically. All right. Is that? Okay. So, okay. So if V is equal to lambda, yes, Stephen, the clean is added here. Wait, what? The clean. Oh, clean star, right? If it was without the clean star, then the language cannot be context free. No, so yeah, so there's a lot of places where I can put the star. I'm not entirely sure where you meant it. So if you meant for some V in AB, then I mean, then that's even easier, right? You can just pick V or A or B, and that's still context free. If you said for some V in AB star, then that's the same sort of result that we were talking about. Okay, if it's, let me just, if it said V is AB star, yeah, that's right. So this is for some, right? But if it said for V in AB star, then because, so the implicit assumption here is that it's for all V in AB star. Okay. So that's, okay. So hopefully I answered Khaled's question. I'm not sure if I did, but it's extremely difficult to keep up with all these questions. Let me answer Kelly's question, and if Khaled, I didn't answer your question, just ask it again, please. If you were to make a PDA, oh, this isn't a question, then you can know you have 2 versus, yeah, so that's proving why it's context free. Can you just explain why V can be set to lambda? Yeah, so, okay. So if I say a string V over AB, okay, over is not the same as in. Over means, you know, the language over the alphabet, a string over the alphabet. So it means all of the possible strings that can be created using the alphabet AB. Okay, so that's the difference. So this is equivalent. This is logically equivalent to a string V in AB star. Okay, that's what it's a string. All right. Okay, so hopefully I answered that. What about what you explained with VV? Yeah, there's not. I feel like in the moment that was probably. Yeah. So again, just I'm setting V to a particular value because it says for some. If V is equal to W, I mean, no, don't make your life more difficult, right? If you can set something, you can set V to be something very easy, right? So that allows you to show that the language is context free. If it's context free for some V, then you've shown the statement. So that's why you don't pick V is equal to W. Okay, Kelly is just, I'm not sure what that, W is in AB, not V. Yes, wait, what? No, W is in AB star, and for some V over AB means for some V in AB star. Okay, they might word things like this, you know, like I mean that's why I did it. Like I wouldn't have put this question if it wasn't plausible. How do we know that V can be lambda? So again, for some tells you that you can pick a particular V. Yeah. Existential crisis. How is WW context free? Okay, whoa, okay, let's calm down with the questions. How is WW, how is W, okay, so WWR is context free, right? Because you can do A as A, B as B, or lambda. So this is a quick proof for why WWR is context free. Where was I? Yeah, okay. If it said V and AB star, then yes. Yes, Renato. For all cases that V is not, can we say that this statement is true? Yeah, so if it was also string V so if it was for some string V in AB plus, so you couldn't have lambda, then it would also be true. It would also be context free. Some is key, yes, very good. If it doesn't need to be for all, it only asks for some, i.e. specific, yes. Right, yeah. Yeah, over is definitely key. Yes, it seems to imply that it's over the alphabet AB. Oh, is that all the questions? Okay. Yeah, no. Okay, all right, okay. Okay, a string V over AB is logically equivalent to V is in AB star. Okay, that's what it means. That is not more complicated than this. All right. Okay, if I missed any questions, let me know. So yeah, so that's why I said the main idea to take away is set notation. So some for some was the key here. It's for some particular V that you can pick was what made it context free. Okay. All right. So if there are no more questions about this, I agree that this is a tricky question, but this is a tricky course, right? So that's why I wanted to include it. All right. So I feel like it's good. Yes. Yes, V can be, so it's a string V over AB means V is in AB star. That means that V can be any string over the alphabet AB. It means V can be any string in AB star. So V can be lambda, V can be A, B, A, B, BA, BB, and so on. Well, a string V over the language means it's using the alphabet AB to create the string. Okay. V can be of any length. Yes. Yes, it can. All right. Any other questions about this?
I have a question. So basically, when we're asked, like in that
Yes.
is the language context free or not, what's the
Yes.
first thing we should try doing? We should try finding a context free grammar.
Yes. Yes. You should. If that's easy for you to do. Yeah. So that's a good question. If it says is L a context free language, so the steps you could take, sort of, you can do this in kind of two directions. If you think it's true, you could start by trying to find a context-free grammar that's going to generate it, or you can also find an NPDA if that's easier for you. Okay, and if that looks like it's pretty hopeless, then also in the same direction, you could start from sort of all the way to the sort of other direction. You could start looking
Pumping lemma?
for for W in the pumping lemma. And sort of the idea is try to make these two things meet. And if sort of hopefully if you kind of get stuck in each one, you can sort of pinpoint more accurately which one it is, and then allow you to determine whether or not it's context free. Yeah. Does that make sense?
Yeah.
Okay.
Thanks.
No problem. What did this for sure? I mean, it's not going to be an impossible language, right? I mean, they're not. The professors aren't crazy. They're going to give you something that they know is reasonable. It's just that you need to find the trick for it to be reasonable, right? So if you think that a question is impossible, then the most likely thing that's going on is you're missing the trick. Yeah, from my experience, from seeing the different quizzes and things like that. Okay, but yeah, that's a good point. All right. So any other questions about this? Nope. Nope. Doesn't look like it. All right. Yes.
I'm sorry.
Yes.
Can we go back to the question?
Yeah. So it's a mess now. Okay. You want me to erase? Do you want me to erase?
So you mean if V is not lambda, then this language is not a context-free language, right?
No. It can still be context-free if V is not lambda. So if you set V to A, then what would you have? You would have WAAWR, right? And then you can also create a so you can also create a context-free grammar for this. You could just do S is ASA, B as B, and then finish off with AA. Right, so that would also give you this is the reverse of this, and that would work fine. So it doesn't need to be a lambda, but it just helps with the explanation.
Okay, so actually for this language, it's always context-free.
Okay, so I think, yeah. So the fact that you can find one V means that the language itself is context-free. So, I mean, you shouldn't be saying that it's always context-free. If it's context-free, then by definition, it's always context-free. There isn't an always. If you've picked a V, so that means it is context-free. Okay?
So if we can pick up a V that makes this language is not context-free, then this statement is true.
Yes, exactly.
So
well, no, actually, no, not exactly. So that's a good point. So you're not allowed to say that you can pick a V to make it not context-free. If you can just find some V, because that's the definition of the language. If you can find some V to set this and find a context-free grammar for it, then it becomes context-free. You can't do the opposite. Because I think I saw where you were heading with that, so you can't do that.
Okay. Thank you.
No problem. Okay. Yeah, so Carl, we're still at the same file, which, that's not a bad thing. We're at exercise 7. Kelly, if you know that WWR is context-free, yes. Yes, very good. Yes, very good, Kelly. Stephen, but you could choose a V. No, so yeah. Yeah, so that's what the person was asking. You can't do that because it's saying for at least one V. If you can find at least one V to make it true, to make it context-free, then it's by definition, the language becomes context-free. Okay, so for some, remember from your 232, for some is equivalent to there exists at least one V. So that's the same thing. It's for some V means that there exists some particular V that you can pick to make the language context-free. So that's why you can't you can't say, oh, I can, so that means I can pick another V to make it not context free. No, you can't do that. The question says the language is not context free, which is false because the language is context free. So it's like a double negation. No? Yes? Maybe? No, I feel like you're still confused. So it's saying L is not context free. And you showed that L is context free, right? So that means that this statement is false. No? So if this still isn't clear, we can maybe talk at the end of the session. Okay? Okay, Stephen? So if it's still not clear, I don't mind staying after. Yeah, okay. All right. So actually, just because of time, so the next question was about converting grammars to a Chomsky normal form. I'm kind of thinking of skipping this one because of how, there's not really a trick here. And because the solution is there. So I don't know how everyone feels about that, but maybe just as a reminder, how do you show that a grammar is, how do you convert a grammar to Chomsky normal form, right? The first thing is you need to simplify the grammar. So remove the lambda productions, then remove the unit productions, then remove the useless productions. So you do that, it's pretty mechanical. And then the second thing you do is convert to actual CNF. And how do you do that? Well, if you have something like X gives you A, B, I don't know, Y, B, then what you need to do is you have TA gives you A, TB gives you B. So you create two auxiliary variables. Then this becomes X gives you TA, TB, Y, TB. And then you use the trick where you say, okay, this is going to be my first variable, V1. So V1 is going to be TB, Y, TB. Then my second variable, V2, is going to be this. V2 is going to be, V2 is going to be Y, TB. And then, so that means I can replace this with V2, and I can replace this with V1, and then that gives you a Chomsky normal form. So that's just a reminder of how do you do it. And, this is pretty mechanical. So once you do like one or two, you're usually pretty safe for these types of questions. The only thing I want to say about just the normal forms is, make sure you know the definitions of Chomsky normal form and Grayback normal form. Typically, it's not asked to convert to Grayback normal form because the algorithm is a bit more complex, and so they don't ask you about that. But they do ask you things, more theoretical things like, know the difference between GNF and CNF, and what does it mean if a grammar is both in CNF and GNF, let's say. So you can try to think about that. Okay, but if no one has any objections and no one's really mad about it, I'm just going to say that's how you do it, and the solution is here, and it's a pretty standard question. I feel like if it was just Chomsky normal form in the final, everyone would be very happy. So that's my reason. All right. So I think that's good. Okay. Question 9. Question 9 is actually good. Let's try to take a minute. What time is it? Yeah. So I think we'll probably be done in next half an hour. So try to take a minute to look at it, and we'll go over the solution together. All right, so hopefully you had time to at least read the questions. Let's look at it together. So this is a question just in general about PDAs. So, you know, just as a reminder, if you have a PDA-M, again, its functionality is the same for, its functionality is used for the same thing as FAs, in the sense that you give it a string and the machine either tells you yes or no. Okay, so that's the point of it's also an acceptor, except that now what you're doing is you're giving it some memory, you're giving it a stack, and you're allowed to push and pop to the stack however you want. Okay, so now we have some statements about what are PDAs and specifically N and D PDAs. Okay, so the first one is every NFA has a corresponding Dpda. So that is, if you just remember your diagram, this is a set of regular languages, and this is the set of deterministic context-free languages, right? Which is equal. So the set of deterministic context-free languages is equal to the set of languages accepted by DPDAs. So this is, the regular languages are a proper subset of the languages accepted by DPDAs, meaning that if you have a regular language that's accepted by some NFA, then what you can do essentially is you can tell the NFA, don't use the stack, right? And if you don't use the stack, but you give it a stack and it doesn't use it, then that is a corresponding, so it might be a corresponding NPDA, but every NFA is also has a corresponding DFA, so it would have a corresponding DPDA. Okay, but I mean, if you don't get that part, you can just sort of think of this diagram, and it should become immediately clear that yes, this is true. Okay. So no questions about that? No, it looks like no. All right. Exercise 9, question B. So the next one is every DPDA whose stack grows to at most 10 has a corresponding DFA. So in fact, this could have been any finite number. So it could have been something like, I don't know, 335, or it could have been a finite number. If the stack in your DPDA has a fixed amount, so meaning that it has a fixed size, that means that you're essentially just using the stack as a convenience. And in fact, everything that you're doing with the stack can be done in sort of a more complicated fashion with an FA, so either a DFA or an NFA. Okay, so what that means essentially, what I'm trying to say essentially is that DPDAs who use a finite amount of stack are essentially not using the stack as it would be powerful, or as powerful for a regular PDA, because for a regular PDA the stack can grow arbitrarily, but for a DPDA where you fix the size of the stack, it has a limit. So that means you can essentially make the DPDA transitions, all of them, you can make them into DFA transitions. Okay, so what this also means really is it's saying that a language over this kind of DPDA, over M prime. So let's call this, if this is M prime, so a language over M prime is actually going to be regular. Okay, so so that's why B is also true. Okay? So Jenna asks, are we treating NFA as a NPDA here for A? No, so I see why you're asking the question. So we're not because an NFA, if you directly converted it to a PDA, it could have some kind of, choice. But what you could do is you could take your NFA and then convert it to a DFA, and then a DFA that doesn't use its stack is a DPDA. Okay, so that's how you would, that's the kind of reasoning you would go through. All right. So I hope that's clear. For C, we have the statement that every NPDA where no lambda transitions are used has a corresponding DPDA. So if you know the definition of a DPDA, this is immediately, so this is true, this is true, this is immediately going to be false, okay? And the reason for that is you don't just need lambda transitions for something to be non-deterministic. If you have, let's say, a state, and you have essentially two choices. So if you read an A and you have the $, you could push an A and go here. Or if you have an A and the $, at the top of your stack, then you could push a B and go here. Excuse me. So you have two choices. The fact that you have two choices means that it is non-deterministic. And so this NPDA does not have a corresponding DPDA. So it's not also a DPDA. Okay. So that's why C is false. All right. And the last one is a DPDA cannot have any lambda transitions. So again, if you know the DPDA definition, this is also going to be false. And the reason for that is the only thing that DPDAs are really forcing you to have is for every transition you have, you can only have one choice. And so if you're here and you just read a lambda, right, just consider this as a lambda transition, this is still a DPDA because for any string that you have only one choice. And the choice is you're going to go from here, you're not going to read anything, and you're going to go here. So there's one choice, meaning that it's a DPDA, but it does have a lambda transition. So that's why this is false. Okay, so any questions about this? B would still be true for any, yes, very good. So if this was like 1071, then it would still be true. Because just think of the stack as helping you make a very compact DFA, right? It just allows you to keep things very tight. So an example for that is, remember AN, BN, for n less than or equal to 335, right? This is regular, right? What you could do to make it a PDA that was actually an FA is you would just say, okay, I'm going to use a stack, but I'm going to limit my stack to 335 symbols. Okay, and so then this kind of shows you why if the stack has a fixed size, then it's actually accepting a regular language. So for any fixed integer b, it would be true. If the stack was not finite, so I'm going to erase this. If this said grows arbitrarily large, meaning that you don't set a limit on the stack, then that means that you're actually using the power of your stack completely, and so that's not equivalent to a DFA. Okay, so for any fixed integer b is true. Could you explain why C is false? Yes. I feel like two people had, yeah. So every NPDA where no lambda transitions are used has a corresponding DPDA. So the fact that your NPDA does not have any lambda transitions does not mean that it's deterministic, does not mean that it's non-deterministic. Okay. Wait, sorry, let me say that again. If you have an NPDA that has no lambda transitions, then it doesn't mean that it's deterministic. Okay. So, and the reason for why that's true is because, for instance, here, if you start here and you read an A and you have a $sign, then you have two choices, right? So if you have two choices, then it's still non-deterministic. Okay. So that's why C is false. All right. Difference between DPDA. Okay. Yeah. So difference between DPDA and NPDA, it is well explained in the lecture. I also have a tutorial video on YouTube that explains it. But the major thing you need to know about DPDAs is you cannot have, at any point in time, you cannot have a choice. Okay. So that's what deterministic means, just in general. The next step that you go to is deterministic. It's set in time. You don't have any kind of wiggle room. So, but if you want the definition, then the definition is that for every transition, if you have a transition where you're reading an A, you see a B, and you go to and you're at P. Let's say, so you're at Q. So let's say you're here, you're reading an A, and you have a B at the top of your stack. Let's say you're doing this. Then the size of this has to be at most 1, basically. So you can't have another transition that does something like this. So you can have 2 different choices. Okay. So that's the first thing. And the second thing is if when you read a lambda, so if this is greater or equal, if this is greater or equal to 1, so in other words, if it's not empty, then you can't have any other transitions with B at the top of the stack. Okay, so that's those for a PDA to be a DPDA, for M to be a DPDA, it needs to respect these two rules for every possible transition. Okay, but yeah, I agree. It also is it's explained in a few places, including my tutorial. So yeah. All right. So any other questions about this before we move on? I don't think I skipped anyone. No, I didn't. All right.
I still don't understand
Yeah.
why B is true.
Yeah, no, that's fine. Sorry, just I have my voice is dying again. The reason why, so let me just go back here. If you have, let's say you have a machine here, M, and it's using a stack, right? But the stack has a limit, right? So your stack can go above, it can't go above a certain number of symbols. What that means, essentially, is that you're not using the full power of your stack, right? It's as if you had a program that was running on memory, but the memory would always stop at, like, let's say 10 megabytes, right? So if it always stopped at 10 megabytes, then you're constrained in what types of programs you can write. And so if you think about the PDAs as the types of programs, then the fact that you have a limited amount of memory means that the PDAs you can write are very limited. And in fact, the PDAs that you're writing are all equivalent to FAs, because they can't use any more resources than a fixed amount of space. So It's the fact that you have a fixed amount of space that sort of makes the PDA not use all of its power. And the fact that it's not using all of its power means that it's equivalent. It's just as it's just as powerful as an FA. Okay, so
Okay.
is that clear?
Yeah, it's really clear now.
Okay, okay, very good. Any other questions? No? All right. The next ones are fun. Well, they're fun for, well, you'll see. All right, so let's move on. So that was about, what, did I want to say something about this in general? Yeah, so definitely for DPDAs and NPDAs, know the definitions very well. So if you're confused about the definitions, please go watch the lecture again. And also, if that's not still clear, then I have a tutorial either on the Moodle or on YouTube for DPDAs. The definition is very important to know. And so, yeah, so it's important to know the difference between NPDAs and DPDAs. All right. So the next questions are, again, kind of closure property questions, but now they're about deterministic and, what is it? Deterministic and non-deterministic context-free languages. So while you answer that, I'm gonna answer Jenny's question and post the link on the chat. So I'm gonna try to do both exercises 10 and 11. So try to do both. I'll give you 2 minutes, 3 minutes. All right, never mind. So that's the link for the YouTube. Okay. All right. So excuse me. Hopefully you had some time to look at the questions. I know someone has their hand up. I don't know if that was from before, but I just noticed it. So if you do, then you can ask your question, but if it was from before, then it's fine. Yeah, no, okay, I guess it was from before. All right, so the first question is an interesting question. It's a true or false, saying that deterministic context-free languages are not closed under the complement. So this one is actually, oh, okay, wait a minute, let me answer those questions first. For CNF, yeah, sure. I can do that. If I don't, well, no, I'll probably see it. So yeah, I can do that. So DCFLs are not closed under the complement. So what is, okay, so what is it asking? It's saying, suppose you have an arbitrary deterministic context-free language L. So L is deterministic context-free. Is L complement deterministic context-free? Okay, so this is extremely not obvious. Like there's no real way that you can, well, I don't know. I had to think about this really hard, but it turns out that deterministic context-free languages are closed for sort of all of the useful operations. They're going to be only closed under the complement, and this is very surprising. So for deterministic context-free languages, L complement is also going to be deterministic context-free. And I'm not going to give you a proof because that would be painful for everyone. I'm going to give you the intuition though. So L, AN, BN. So let me give you an example of a deterministic context-free language. So I have L is AN, BN for n greater or equal to 1. This is deterministic context-free because, so this is DCFL. Because there exists a DPDA, there exists a DPDA that accepts it, and that DPDA is going to be, you're going to start with an A. You need to start with an A because n has to be at least 1. So you're going to just push 1x on top of it, and then you're going to push the same number of A's as B's. So this is, I'm hoping everyone is pretty comfortable with this DPDA. So you're going to push the same number of A's as B's. So you're going to push a bunch of A's. And then once you see your first B, you're going to pop it. And then you're going to pop all the other B's, right? You're going to do that, right? You're going to keep doing that all the way until you have nothing else to read and you have a $sign at the top of your stack, at which point you're going to go to the final state. Okay, so L is deterministic context-free. So L complement is also going to be, so the claim is that L complement is also deterministic context-free. And in fact, you can prove this by actually using this machine to create a new machine that's going to accept L complement. And that machine is actually going to be just the same trick you do for L complement in a DFA. You can actually use that same trick for DPDAs. So what I mean by that is you can convert all of the non-final states to final states. So you can do this. So converting, so using the same exact transitions, but converting all of the final states to non-final states and all of the non-final states to final states. This guy, this machine here, let's call it M prime, is actually going to accept, so this M prime is going to accept the complement of L. So what's the complement of L? It's a bunch of A's. So, right. So, I mean, you know, ignoring the starting with B and ending with whatever, part of what L complement is going to be, is it's going to contain AN, BM for N. So this is a subset of the complement, but AN, BM for N different than M. So this is a subset of L complement, and this is what makes L complement also not regular. So this is what makes it a challenging language to accept. But if you look at this, DPDA, this DPDA is actually going to accept this language. Okay, so why is that true? Because it's going to accept every possible configuration of AN, BM, where you don't end up removing the same number, pushing the same number of A's as popping the same number of B's. Okay, so because so let me give you a test run. So someone said AB. Let's say you're given AB, right? Yeah. Okay. So if you're given AB, right, and you run through this, n prime. So you go from here to here, and you push an X to your stack. Then you don't use this transition. You read the other B. You pop this, right, and now you have the $sign. And now you can use this lambda transition. Remember, it's deterministic. So you can use this lambda transition to go to your non-final state. And because you end in a non-final state, then AB is not accepted. But if you have something like AAB, right, then what's going to happen is at the end, you're going to have an extra X, right? You're going to have an extra X, and that's going to prevent you from going to the non-final state, and that's going to allow you to stay in a final state, which is going to allow you to accept AAB. Okay, so this I mean, this isn't a formal proof, but this shows that. So just to answer the question, what does closed mean? This shows that if L is deterministic context free, then so is L complement. Okay, this is what it means for this is what it means for deterministic context free languages to be closed under the complement. That's what it means. Okay. So yeah, so you can use this trick to find a part of the language, and in fact, the part of the language that makes your language context free. You can find a machine that's going to accept that part of the language. Okay, so this guy can be accepted by this machine, and you can find that just by sort of complementing. By sort of complementing like you do with DFAs and NFAs, the DPDA on the left. Okay, so this is a pretty surprising result, which I thought was important for you to know. Okay, so any questions about that? That's a good question. Yes. So that's the case for it's the case for deterministic PDAs because in deterministic PDAs you have a single choice, and so because there's only one option, once you get here and you finish reading the string, because you have a $sign at the top, there's no option for staying, right? So the only thing you can do is move on to the next state. So there's yeah. So that's why in this case here you need to take it. Yeah, no problem. All right.
I have a question.
Yes.
So when you want to draw a L complement, it's the same thing, but we just change the final states to initial state?
So it's not quite the same thing because L, if you
the first three states in L complement, it's final,
yeah.
like exception state, right?
Yeah. It's the only thing that's missing here is because here L is ANBN. The complement of L is when the two are different, and also if you start with a B. So if you start with a B, then you would have to add a transition here. But the major difficulty, right? The major a part of the language that's difficult to create for is A and B and different than M. So the fact that you can find a machine for this that's also a DPDA allows you to say that the whole thing is a DPDA. Or sorry, the whole thing is a DPDA.
So did you draw? So this is the one you drew. That's L complement, right?
So no, sorry. This is a DPDA that accepts this language, right?
Okay.
If you wanted to add if you wanted to create the machine that accepted L complement, all of L complement, and then what you could do is you could just add a B transition here, right? And then you don't care what happens after there's a B. So then you could just say, just accept everything. You could just do this. So if you add this, then that becomes a full DPDA for accepting L complement.
Okay.
But my point here was just that this complementation allows you, like changing the final to non-final and vice versa. That allows you to find the thing that makes the part of the language that makes it difficult for you to accept can be handled by this flipping of states. And then to that, you can just kind of do a bit of a cleaning, and that also gives you a DPDA. All right?
Okay, yeah.
Okay. Yeah, so I don't want anyone to be under the impression that M prime is a machine that accepts L complement. It's a machine that accepts this, okay? Which is the biggest piece of the puzzle for L complement, right? Because the rest is fairly easy because you could just use this part. All right. Did I want to say something about this? Yeah, so again, the complement is the only operation, the only sort of main operators. I mean, there's a few weird ones, but it's the main operation that under which deterministic context-free languages are closed. So they're not closed under the union or the intersection or the star operation, but they are closed under the complement. Okay. So that's a pretty important fact to know. Yeah, so that's all I wanted to say about exercise 10. Okay, so I hope that's good. I'm gonna erase this. So I'm gonna erase this top part here. Just so you know everything is visible. So the next question was kind of a similar flavor. It was about determining if the given language that we have is a deterministic context free or not. So, oh, well, I mean, if you want the answer, right, for 10, DCFLs are closed under the complement. So that's why this is false, all right? Okay, so exercise 11, true or false, is this language deterministic context free? So what we're given is we're given AN, BM, CK, where either n is equal to m or m is equal to k. Okay, and so if anyone's intuition told them that this is not deterministic, well, that intuition, sort of just the intuition that this sort of, you have kind of two choices at the start. So once you start creating your DPDA, right, just, I'm not going to do it, but once you start creating your DPDA, you kind of have two distinct machines that you're going to want to use. You're going to want to use the one for AN, BN, CK, and you're also going to want to use the one for AN, BM, CM. And so the non-determinism is going to help a lot here, because it's going to allow you to know which one of the two machines, which one of the two branches you need to go to, right? So the fact that you need to make the fact that the machine has to guess means that it's impossible for this to be deterministic. And so that's why this is non-deterministic. So that's a pretty hand-wavy reason, but that's actually the correct reasoning for why it's non-deterministic. So that's why is not DCF, so is not deterministic context-free. That's true. Okay, because as I said, you need to make two choices from the very beginning of your machine. Okay, and what's interesting to notice is, like I just said before, this language here, L1, is deterministic context-free, and this language, L2 here, is deterministic context-free. But you can see that the union of the two is not deterministic context-free. So I know some of you probably know this because this was in one of your quizzes, but this is just kind of a reason for why that's true. All right, so any questions about this?
Yeah, I have a question.
Yes.
In which slides did the prof talk about closure properties of DCFL? Because
Yeah, so they don't.
they don't, right?
No, they don't.
I thought so, because I could not
Yeah.
find it. I just checked the slides. We only see the closure properties of CFL only.
Yeah, so that's why I thought it was important to talk about, because they don't, and they might test you on it. So yeah.
Okay, thanks a lot.
Yeah, no problem. All right, so then I think there was a question about CNF and GNF. So for CNF, you mentioned that we should focus. Oh, no, okay, I see. Okay. You know, I didn't mean if you have a CNF, then go to GNF. I mostly meant what's the definition. So I mostly meant what's the definition of a CNF, what's the definition of a GNF. And for instance, what does it mean if a grammar is both in CNF and GNF? Okay, so I mean remember what does CNF mean? It means that all your production rules look like A gives you BC or A gives you little a, and then the GNF is don't want to say anything dumb. No leftmost variables. Yeah, so it's a, yeah, so it's a y, and then y can be sort of any string of variables, right? So if this is true, if they're both in CNF and GNF, then yeah, so yeah, so so no leftmost variables is right. So you can't, essentially you can't ever have a variable sort of at the left of this guy. I mean, technically speaking, for something to be both in CNF and GNF, it would mean that because GNF enforces a terminal here, right? And because CNF enforces either a terminal or two variables, so these are variables, then the only thing that you could have, the only production rules that you could have would be something like X gives you some terminal string. Okay, if you have x gives you some terminal string, so let's say x gives you a or x gives you b. Although this is a pretty useless grammar, this is what would happen if you sort of took a grammar that was in CNF and a grammar that was in GNF, and you said they need to be in both, because remember, GNF has to start with a terminal string. So you have to start with a terminal string, but then you can't have any variables after that, because that would violate this part of CNF. So that's why you need something that only looks like that. But yeah, you would also not have any leftmost variables, or you wouldn't have any variables, basically. Okay, so that was one example about, kind of understanding the difference between CNF and GNF. It's if you can come up with a question like this and then solve it, then that means that you've probably understood the fundamental differences between the two. Okay, so is that good? I think that's good. I don't think there, yeah, so, but if there are questions, I mean, of course, let me know. I don't have anywhere to go, so yeah. No? Okay. All right. So if there are no other questions, there's 3 more. There's 2 on pumping lemma for context free, and then there's 1 Turing machine. I might skip I wanted to do an explanation, but it's probably not important. The lectures are pretty good for explaining some of the more theoretical stuff. Yeah. So maybe take a minute to try this question, and then we can look at it together. All right, so there's some nice discussion here, which is nice. I like that. So what do people think it is? A lot of people think it's C. Some people say A, D. A and D are in the language, but they don't involve C, which you'll need to, yeah, okay. All right, so it seems like most people have understood it. So we want to use the pumping lemma to show, so this is a reminder from the very beginning of the session, to show that the language here is not context-free. So remember, let me redraw the diagram that you've seen, in this case, 12 times now. So this is a set of regular languages. This is a set of deterministic context-free languages. This is the set of context-free languages. And now we want to be somewhere here. So how do you show that you're somewhere there? You need to use the pumping lemma for context-free languages. And remember, how the pumping lemma goes is, you pick a string, and now what you're doing is you need to decompose it. So what is it? UV, sorry. Come on, UV, X, Y, Z, and then you're pumping these two guys, right? You're going to pump them up or down. And what you need to do is you need to consider all the possible cases. So let's look at the, okay, let's start with the ones that are well, let's look at the one that's definitely wrong. B is not going to work out just because this is not in L, right? So, I mean, immediately, if the string isn't in L, then you haven't picked the correct string. The A, okay, so is not obvious, but A is also not going to be right. So this definitely belongs to the language, right? But yeah, I'll answer that question in a second. But for A, if you decompose it into certain cases, you're going to get cases where it's impossible to get a contradiction. So now this is going to, hopefully everyone can follow me here because this is going to require a bit more concentration. So if you have AM, BM plus 1, so that's going to be, come on, A, and then B, B. So you have MAs and you have MBs. So now remember what you do in trying to prove that a language is not context-free. You're taking U, V, X, Y, Z, and you're scanning it over the whole string. So one of the possible scans could be you could have a U is here, then V is here, then X is here, U, V, X, and Y is here, and then Z is here, right? So what that means is you could have V is AK1 and Y is AK2, right? MB should be, yes, very good, thank you. Thank you, Stephen. So you have, so essentially V has K1As and Y has K2Bs, right? So now remember the next step is you're going to want to pump up or down. So remember you can't pick the particular K1 and K2. You can only say that, okay, V has some number of A's and Y has some number of A's, but you don't choose the number of A's that V and, sorry, come on, Y should be B's. Sorry about that. So clearly Y is a bunch of B's, right? Hopefully I haven't confused anyone because Y is within the B's, so Y should be B to the K2. All right, so what I want to say is the lemma isn't telling you that you have to pick a specific number of A's for V and a specific number of B's for Y, okay? And so that means that you could, your opponent, imagine you have an imaginary opponent that you're trying to work against to show that a language is not context-free. Imagine that opponent says, okay, well, you set the V and Y, but now let's say I'm gonna try my hardest to break your argument. Let's say I say K1 is equal to K2, okay? Now what's gonna happen if I pump up or down? So if I pump down, remember what W0 is, it's U, V0, X, Y0, Z. So that's just going to be A, M minus K1, B, M plus 1 minus K2. And so because these two are equal, this does not lead to a contradiction because the number of B's here is still greater than the number of A's here. And similarly, if you pump up, so you have U, V2, X, Y2, Z, then you're going to get A, M plus K1, B, M plus 1 plus K2. Because K1 and K2 are the same, again, the number of B's is still greater, strictly greater than the number of A's. And so this does not lead to a contradiction. This is still an L. And so is this, right? So you haven't gotten a contradiction. And in fact, for this particular choice of W, you cannot get a contradiction. Because you cannot get a contradiction, it means that it doesn't mean that your language is context-free. It means that you picked the incorrect string to pump. Okay, so that's why, hopefully that was clear. That's why AM BM plus 1 is an incorrect choice for W. So it would not work. And so that's why this would also not work. And then so D is also going to be wrong. And it's going to be wrong for a similar reason. So let's say you have W is BM, right? In this case, you have you have U, V, X, Y, Z. So now the V and the Y's are all B's, right? So now, if your opponent chooses to pump down, right, then your opponent could pump down all the way so that you could get B M minus K1, M minus K2, where then you could have possibly that K1 and K2 are equal to M. And so then you could somehow, if your opponent was very clever, you could get the empty string. And if you got the empty string, then this would not be true, right? The number of A's would be equal to the number of B's, would be equal to the number of C's. And that would mean that your pumping failed, basically. And so, although if you pumped up, does anyone see something wrong with my argument? Because there might be something wrong. Because if you, oh, right, yeah, all right, okay. So no, okay, sorry. So if you chose to pump down, this would happen, and so yeah, sorry. I might have confused you. Sorry. Let me start over. So if you were to pump down, again, you wouldn't know how to choose your K1s and your K2s. And so what could happen is you could just have some, yeah, so lambda was the incorrect conclusion. If you had something like B M minus K1, K2 for something greater than 0, then this would still be an L, and that wouldn't be a contradiction, okay? If you pumped up, well, of course, if you pump up, this condition is still going to be true, and you're not going to have a contradiction either. So in either case, it's possible that you don't get a contradiction, and because of that, it's also an invalid choice for, W. Yeah. So sorry, I mixed myself up there. So yeah, so as some people were saying, C is correct. You could pick C, and then for every possible decomposition, you would be able to derive a contradiction, because you could pump up if it was just A's, you could pump up if it was just C's, you could pump down if it was just B's, and then if it was in between, you could pump up to get a different number of, so a smaller number of B's as C's, and also here you could pump down to get a smaller number of B's as A's. So I mean, if you do that sort of computation in your head, then it would work. Yeah, so I kind of foresaw that I would need to explain D because I didn't explain it well. But I think someone asked a question before that. If for B, Cm plus 1 is Cm, yes, that would work. Yes. So if it was Cm instead, then that would have been fine. Yeah, that would have been good. Yeah, so David, and I'm sure I'm speaking to everyone when I'm saying I have to re-explain D. For D, can you explain why if you pump down and got lambda? Yeah, so if you pump down and you got lambda, I was wrong. So I made a mistake in saying that it wouldn't work. Actually, the only way, if you would pump down, the only way you could get a contradiction was if you got that it was equal to lambda. Because if you got that it was equal to lambda, then the number of A's would equal the number of B's, and that would equal the number of C's. So, in fact, this is the only way. Yes, you can only pump down once, but for example, you could have a fluke situation where K1 plus K2 was equal to M, right? And then it's possible that you pump down and you got B to the 0 and then lambda. However, okay, this is a big but, you can't claim this. You can't be certain of this. And so because you can't be certain of this, you can't guarantee that this is always going to work. Okay, you can't always say for every possible setting, you're always going to get sort of a reduction to lambda. You could get a reduction to maybe B1 or B2. And in that case, you would not get a contradiction, meaning that your argument was incorrect. Okay, so so what I was trying to say here is, yes, exactly. The adversary, very good. The adversary is the one that chooses the length of K1 and K2. So, I mean, K1, your adversary isn't going to be nice, right? He's not going to be nice and say, okay, I'm going to let you pick M, and then I'm going to let you get a contradiction. No, he wants to prevent you as much as possible, he or she wants to prevent you as much as possible from getting a contradiction. And so that's why they would pick something like less than M, and then you wouldn't get a contradiction. Okay, so yeah, I mean, I don't know, it's helpful for me. It's always helpful for me to think of in the pumping lemma for the regular languages, and also for here, you have an opponent that's working against you, and they're the ones that pick K1 and K2. And so if they're trying to be very nasty, then you can sort of determine whether or not the string that you picked can lead to a contradiction in every possible case. Okay, so you want to be able to trick the opponent. You want to be able to trick the setting of your V and Y for every possible decomposition. All right. So hopefully that's clear. Sorry about the initial mistake. For option C, if we put down, for the case of only B's, number of B's can still be greater than M. No, because remember, the other thing you can pick is WI. So you can pick the I. You can't pick the K, so you can't say how many B's your V and Y have, but you can say by how much you're going to pump down. And so if you pump down by at least 5, so if you wait a minute, you can't. All right, give me a second. No, you can't pump down by more than 1. Because you can only have yeah. No, that's very fair. That's a good point. Yeah, so the point is, oh, that's very good. The point is that if you have AM, B, M plus 5, C, M, then if you just have V and Y's within the B's, then your opponent, yeah, very good. Your opponent could be very nasty and say, could say, so V and Y could just be B1, let's say, and then you couldn't pump down more than once, right? So then, yeah, so I'm afraid actually even this case would not work. Yeah, so that's a very good point. yeah, I hope everyone sees why. Because you can't pump down more than once, right? So you can only go to W0, right? And because you can only go to W0, then you can only subtract, you can only subtract K1 and K2 once. Yeah, sorry, I'm thinking at the same time as I'm speaking. Yeah, so because if you did minus K1 minus K2, there's no guarantee that K1 and K2 is going to be greater or equal to 5. So that wouldn't work either. Yeah, that's right. Yeah, that's right. Yeah, I'm very happy someone saw that. But yeah, as someone said, instead of picking n plus 5, the better thing to do would be picking n plus 1. So actually, all of these choices are not right, which means I'm gonna change this. So this is wrong. So actually one of the only possible choices would be AM, BM plus 1, and CM. Yeah, that's right. Yeah. So none of them are right, which hopefully doesn't happen to you guys. Sorry about that. Yeah. So I hope everyone sees that though, because the fact that you're playing against an opponent is what kind of just made me click that that's not right. Yeah, so hopefully, yeah, exactly, very good. There's room, yeah, that's the best way of putting it. There's room for there not to be a contradiction. So because if let's say your opponent was, you know, very mean and he said, okay, I'm just going to say that the sum is 4, right? You don't know what's going on, but if they say, okay, the sum is 4, then you still have AM, BM plus 1, CM. And so that's still within this language L. So there's no contradiction yet. And so for that, for that decomposition where you just have V's and Y's and B's, you don't get a contradiction for an arbitrary setting of V and Y, which means that the setting of W was initially incorrect. So yeah, but that's the best way of saying it. There's room, there's a possibility for there not to be a contradiction. So that's why it's incorrect. And so that's why this is in fact the only and the best way of showing that it's not context free. All right. So yeah, well, that was very, thank you for spotting that. Very good. Okay. I feel like that was a good learning experience for everyone, including me. That the previous pumping limit, since there was room. So what was the previous? No, so that one's fine because so if we just go back 2 seconds, that one's fine because you can pump up to get a contradiction, and you can pump up. You can pick WM, right? You can pick WM to be so that you can get A to M, B to M, right? At least, right? You can pick your pumping number so that you can get a contradiction. Here, I'm not setting, there's no restriction on what K has to be, okay? Because, yeah, so there's no setting on what K has to be. I'm just saying that if you pump at least M times, then you're going to get a string where the number of A's is at least greater than or equal than the number of B's. But this is a very different proof because it's over regular languages. So the one for regular languages is a lot more forgiving than one for context-free languages. All right. So so yeah, no, it doesn't mess up here because here you're not adding, so you're not saying it's M plus a specific number, right? If you say it's at least, if you're gonna add at least M here, then you're at least going to have M there, okay? It could be more, but it certainly can't be less if you're pumping up m times, right? So that's why that worked. Okay, yeah, okay. All right, so I'm gonna have to change this. All right, so there's another pumping lemma question. And now, yeah, so now it's with the correct setting. Okay, so I'll give you a second to try this. This one's actually a bit easier, I find. I think this one's easier than the last one. So a minute
This
again.
one-
Yeah.
So,
Yeah.
Sorry,
Yeah.
exercise 13.
Yeah.
I'm not sure. There might be a typo. I looked it over. It seems kind of weird to me, but just as a forewarning.
Let M be the constant in the pumping lemma and consider in examining possible decompositions of which of the functions is incorrect. Where's the typo?
Maybe not a typo, but I feel like the answer is incorrect for this guy.
Okay. 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 Well. Okay. So while you do it for a minute, I'll also do it for a minute and verify that the answer given is the right one. Yeah. But thank you. I'll check it out. All right. So 1 minute. Okay. So I've looked at it fairly carefully. I'm pretty sure. I'm pretty sure it's fine. But I mean, while we discuss it, oh, okay, yeah, all right. So okay, yeah, that's fine. Yeah, that's the typo. Okay, so this should be which of the following statements is correct? All right. Okay. Yeah. So I don't know if that was the typo you're talking about, but
Yeah, that was it.
okay. Yeah. All right. Yeah. Yeah. No. Very good. Thank you.
No problem. I'm glad that I wasn't crazy.
No. Of course not. Yeah. Yeah. All right. Okay. So yeah. So if you were trying to, okay. So I mean, if you were trying to solve for incorrect, then what you should have gotten is, this is incorrect and this is incorrect. But because the correct answer is B, okay, it's the only one that's actually going to give you a contradiction for sure. And so let's just see why A doesn't work. So A doesn't work because, so if you have, a bunch of A's, a bunch of B's, a bunch of C's, and you have your V's here and your Y's here, okay? If you pump up, so if you say V is AK1 and Y is VK2, okay? And no matter how you pump up, you're not certain, you're not for sure certain that K1 is different from K2. Your opponent could be saying, okay, well, I'm going to say that K1 is equal to K2. And then if you pump up, so if you pump up these two, then the number of A's is still going to be strictly less than the number of B's, and the number of B's is still going to be strictly greater than the number of C's. So that's not going to lead to a contradiction. So that's why A is wrong, and because this is a sort of multiple choice, you can use the trick that, you know, if A is wrong, then for sure C has to be wrong, because you have to do it one way, right? You can't do it pumping up, and so it has to be pumping down. Why does it have to be pumping down? Because again, if you have the same setup, right? So you have V, you have Y. If in this case, it won't matter what your opponent sets K1 and K2 to. If you pump down, you're going to get A to the, what are you going to get? A to the M minus K1, and B to the M plus K1 minus K2, and then Cm. And because you're pumping this down, so it doesn't matter if these two are equal, you know for sure that you're going to have the number of B's is less than or equal to the number of C's. So that's going to lead to the contradiction because of this. And that's why you get a contradiction. So it looks like, yeah, so the reasoning, it seems like the reasoning was really because you wanted to get the number of B's less than the number of C's. It wasn't because you can't say the reasoning is because you're going to get the number of A's greater than or equal the number of B's, because if your opponent, sorry, if your opponent did pick K1 equal to K2, then you would not have that situation. And so the actual reason why you're doing that is because you want this to happen, okay? So that's why. So hopefully that's clear. So this one has no typos. I mean, this one, apart from this should have been correct, the answer doesn't have a typo. So yeah. All right. So I hope that's clear. I don't know if there are any questions. Doesn't seem like there are. So if there aren't any, we can keep on going. So this is the last question for the session. I would have been optimistic when I said this was going to take, what did I say? 2.5 hours? Yeah, no. I hope it's been helpful. I know that the last two questions might have been annoying for everyone, because it always annoys me when professors have the wrong solutions. Like, it's like, what the hell are you doing? But yeah, apart from that, okay, thank you. All right, well, I mean, it's not over, right? So then one more question. But yeah, I agree that 30 more minutes was, yeah. Okay, so let's try this one. You're given the font, so you have the same screen. Yeah, so you have the following Turing machine, and you want to know which of the following statements are correct. In this case, there can be none of them correct, one of them correct, or all of them correct, or any combination. Okay, so so try that out, and we'll look at it together. All right. So hopefully you had some time to look at the question. So we have 4 statements, and essentially we need to check if each of them are true or false, basically. So what's the first statement say? It says M loops forever on AA. So M loops forever on AA. So how do you do this? Let me use a different color. So let's say you start. So you have A on your input tape. Remember, in a Turing machine, your initial state, you're always going to start at the beginning of the input tape. Okay, so you start at the beginning of the input tape, and then you use the transitions that are given. So if you start here, and so remember what the transitions for the Turing machines say. This says if you read an A on your input tape, replace it with an A and go to the right. Right, that's what it's saying. So you're at Q0, you're reading an A, you're reading an A, you're reading an A, and so what's going to happen is you're going to write an A, right? So, and then move your pointer, you're going to move your pointer to the right. You're going to go here. So now let's say, so this is Q0, this is Q1. Now you're in Q1. So now that you're in Q1, what's going to happen? What transition can you use? Well, you're in Q1, you're reading an A, you're reading an A. You're going to write an A, right? So this is the only transition that I can use because it's the one that says if you read an A, do something, right? So if you read an A, write an A and then go to the left. So then go back to the left. Okay, so hopefully someone, or almost everyone has seen what's happened. I've essentially gone back to the same place. And so again, if I continue, I'm again going to use this transition to go to the right, and then again to go to the left, and so on, right? And I'm never going to stop. I've in fact found myself in an infinite loop, which don't occur in all the machines we've seen so far, but they do occur in Turing machines. So Turing machines are the first machines where you can have sort of infinite looping on an input. Okay, and so yes, M does loop on AA. Okay, so you got to be careful. You got to trace the input very carefully when you're trying to look at something like this. Okay. What's the next one? The next one is M accepts ACC. So again, let me erase this and this. Let's say this is Q2, and let's say this is Q3. So M accepts ACC. Is this true? So again, set up the input tape, right? You have your input tape, A, C, C. You start at Q0 with A. Then what does it say? It says that if you start at Q0 and you read an A, write an A and then go to the right. So go to the right, and now you're in Q1. So now I'm in Q1, right? Right? So now that I'm in Q1, I'm reading a C. So I'm reading a C. When I read a C, what do? Well, I'm going to write a C and then go to the right. I'm going to move my pointer to the right. So I'm going to move my pointer to the right. And I'm also going to I'm going to go to a new state. I'm going to go to state Q2. So now my pointer is pointing at C, right? So don't get confused. Don't think that it's pointing at the blank symbol right after. It's pointing at C. And so because it's pointing at C, if you read the C and you write a C, let me zoom in a bit, then go to the right. So that's what I'm going to do. I'm going to, oh, come on. I'm going to go to the right, end up in Q3. And because I've ended up in a final state, that means that ACC does get accepted. Okay, so the second one is also correct. All right, so hopefully that's clear so far. What's the next one? Say M accepts AAB. So so that's not going to be true. M accepts AAB. Again, why? Set up your input tape. A, B. So we know what happens. We already know what happens when you read AA. You just go back. You go to Q1 and then you go back to Q0. So you're in Q0 again and you're reading a B. Q0 has no transitions for when you read a B, which means that M halts without finishing the input, which means that M rejects A, B. Okay, so that's why the third one is not true. Okay, hopefully so far so good. The last one, so what is the last one? The last one is L of ABB star. ABB star is a subset of the language accepted by M. So is this true? Well, this is saying that any string that looks like A, B, and then something is going to be accepted by M. So what this particular option is trying to make you realize is that a Turing machine sort of is going to, it accepts a bit differently from PDAs and FAs. If you can get your input, if you can get your input to stop reading here, then it doesn't matter what the rest of your tape has, it's going to be accepted anyway. And so what I mean by that is, let's say I have A and then B on my input tape, right? So I start at Q0, then I move to Q1, right? So now I'm in Q1 and I'm reading a B. I'm reading a B, it tells me to go to the right when I read a B and move to state Q4. So I don't have anything else to do, right? There are no more transitions because remember, for a Turing machine, there are no transitions outgoing a final state. Otherwise, it's not a valid Turing machine. And so because I'm in Q4 and Q4 is a final state, then it's going to accept AB. But it would also accept AB if there was an A here, or if there was, if there was anything here. So B star is weak, is a weak condition. It could have been A, it could have been B, it could have been BA. But in particular, to solve this problem, it could have been B, it could have been BBB, it could have been, you could add any number of Bs, because at the end you finished in a final state, you're going to accept that string, okay? And so that's why this guy is going to be accepted. And so just in general, what I wanted to say about, well, I did want to say something about the pumping lemma. So yeah, so just in general, for like the previous two questions, apart from their quirks, just make sure that you know the formulation of the pumping lemma for context-free languages, also for regular languages, because it's possible that you get sort of a formulation of the pumping lemma that's slightly different, and then you might be asked, is this equivalent, or using this equivalent formulation, try to figure something out, basically. That's why you need to know the pumping lemma, sort of the definition, what does it say, very well, because then you can sort of transition to any other equivalent form very easily. So also for context-free languages, make sure that you know that you have cases, and you have to arrive at contradictions for every possible case, okay? What else did I want to say about? Yeah, so that was pretty much it. So these are essentially pretty standard questions that I think you could get asked for. I mean, because you can't, do a pumping lemma proof, right? So this is something that would probably happen. And so then for Turing machines, what did I want to? For Turing machines, make sure you understand the difference in transition and how sort of strings are, how W are accepted, how strings are accepted versus FAs and PDAs. So what's the difference? Essentially, how is it? Yes, of course, it's using an input tape, but why is the action of accepting different? What makes it different, right? So I think that this example was a good illustration of that. So yeah, so then I got a bunch of emails, well, a bunch, I got one, about sort of the last part of the course, which is a lot more theoretical. You know, you talk about recursive languages, recursively enumerable languages, the different formulation. So there's basically no examples and a lot of theory, right? So in general, it's just very important for you to understand what the sort of, what does it mean for there to be different, how do you say, different constructions of Turing machines, with a stay option, with 2 tapes, things like that. And why is it that why is it that they all lead to equivalent standard Turing machines? Using Turing machines as kind of a computer, like to compute functions. That's something we didn't cover here, but I do cover in the tutorial, and also the other TAs covered. So it's important to know that you can also use a Turing machine to compute functions. So Turing machines to compute functions, and then also Turing machines, the different types. So essentially, really what you need to understand is why are they equivalent? They're equivalent because if you take any Turing machine that has any special gadget, then it's possible to just, if you kind of twist or tweak your standard Turing machine, you can get an equivalent Turing machine. So yeah, and then you saw universal Turing machines, which is just really kind of the theoretical version of a standard computer. So it's a lot more sort of high level stuff, right? Because you can't really be tested on specific examples, like, because you haven't really done any practice on it, right? And then I would say the most important part in the last bit, where you guys talked about, like recursive languages, recursively enumerable, is understand that if you have a recursive language, then it's a proper subset of recursively enumerable. Recursive means that there is a membership algorithm. So the Turing machine is going to say either yes or no. What is it? Recursively enumerable means you have a machine that's going to say yes if W is in the language, but it might not say, it might not halt if it's not, right? And then you can have languages that are outside, where essentially we have no Turing machines to accept that language or that problem. And one of those examples that you saw was the halting problem, which if you didn't understand the explanation on in the lecture, there's a really good explanation on computer file, which explains, like, I don't know, that's how I was able to understand it. So if you just type in computer file halting problem, there's a very nice and very simple explanation to why it works. Anything else I wanted? Yeah, so again, it's very high level after, right? So don't really worry too much about, what exactly does this, like, what would be the run through, like, a stay option kind of machine. And I want to say something else. Oh yeah, and also closure properties for recursively enumerable and recursive languages. Those are very important. So Like, I don't know, for example, if L are E, if you have a recursively enumerable language and you intersected with a regular language, what is that going to give you? To be honest, I haven't thought. I haven't thought of the answer because I just made up this question. My gut feeling is it's probably still in RE, but you would need to, but like try to ask yourself questions like this, because these are very good and very susceptible, very good for multiple choice questions, right? So the idea is try to, you can definitely easily think of questions that are easy to ask in MCQs, and then it'll be easy for them to create variations of those. So then you'll be a bit more ready. Okay. So that's all I wanted to say about that. Now, so yeah, wait, let me think. Yeah. So now I think there was a question about, oh, there you go. There's 40 questions. I didn't know that. No, I had no idea that there was 40 questions. And yeah, I'm not gonna stop recording. Some professors stop recording when they take questions. I don't do that. So can we quickly go back to question 7 for a second? Yes, we can. But I mean, I'm not gonna, so I mean, in terms of the exercises, that's it. If you want to stick around for questions, then feel free. But now I'm just gonna answer, any questions you might have in general. Oh, question 7. This is okay. Yes, sure. I can go over question 7 again. Is there a particular aspect of question 7 that you would like me to look at for the person who asked it? We said it was false. No, so yeah, so we said it was false because it is context free. Yeah, so again, the fact that you can find a V such that, wait. No. So the fact that you can find at least one. So the fact that there exists at least one, right? The fact that there exists at least one V such that you can make this context free means that it is context free. Okay. So no, the answer is correct. It is context free. I know this because I've already seen these questions. I've already seen this particular question, so I kind of know that it's a common trap. So the fact that there exists at least one particular V such that L is context free means that it's context free. So the fact that you could possibly doesn't really change anything, because it says for some V, right? So it says that if you can find a V, so if you can impose a restriction here where you can make L context free, then it is context free. So it's essentially giving you the benefit of the doubt. It's allowing you kind of an easier, because let's say I said, okay, I'm gonna create a context-free grammar for this language. So let's say I just created, I just said S was equal to ASA and BSB and lambda, right? If I said this, I could, this is in fact a context-free grammar that generates this language if I said V, for instance, if say V was equal to lambda. And so the fact that I can create a context-free lambda for a particular, a context-free grammar for a particular setting of V implies that it is context-free. If you can find, remember what the definition of a context-free language is if there exists a context-free grammar such that the grammar generates a language, then it is context-free. So by definition, because I found a grammar where by setting V to lambda, I can get a context-free language, then L is context-free. Okay. So your argument would be correct if this was, for all v. Because if you say for all v, well, that means I can pick a v. In fact, in general, if this was for all v and I just had vv, then I know that vv is not context free. And so that would imply that it was not context free. Okay, so the for some, so again, I know I'm repeating myself, but it's very important. The for some means that you're being allowed to pick a particular v, such that the language is context free. But I mean, really, it's not such that it is. It's saying that yes, it is context free because I can pick that v, right? So so that's, maybe you can think of it that way. It's not such that it is context free. I can do it, right? I can pick the v, so it's context free, right? So I don't know if that's clear. Hopefully it is. Yes, so I'm happy it was helpful. I apologize. I'll fix the typos at the end. I'll fix the typos in the slides. Thank you, Ronaldo, for keeping the morale up. Yeah, I'm not going to end the session. I'm just going to stay around and just wait for questions. But yeah, it was my pleasure. Good luck, everyone. I have a question that's not. Yeah, well, actually, every DFA is equivalent to a Turing. Like, you can just think of a Turing machine as not being able to slide around the input tape, right? Because remember, if this is the set of regular languages, this is a set of context-free languages, and then this is a set of languages. So, if we just say the set of recursively enumerable languages, the set of languages accepted by a Turing machine, but for which there is not necessarily a membership algorithm, this is in here. So of course, if you have a DFA that accepts your language, then you have a corresponding, excuse me, you have a corresponding Turing machine. So yeah, that's a very good analogy. So the DFAs are equivalent to NFAs, right? And then if you think of it as like power, so DPDAs are more powerful than DFAs, and then NPDAs are more powerful than DPDAs, and then Turing machines are the ultimate, so that they provide the ultimate computational power. So yeah, power or strength of the automata. Yeah, so, okay. All right, so no problem, Alex. It's a good question, and it's good to look at the Chomsky hierarchy, make sure you know what's going on. All right, so again, I'm not going to leave. If anyone has questions, I'm going to stick around. Question 5. All right. What was question 5? Oh, the pumping lemma one? Oh, this one. Right, okay. What does language over sigma mean? Wait, are you sure that was about question 5 or is it about question 7? What does language over, oh, no, here. Right, yes, no, that's a fair question. It's very similar to string. String over sigma means, you can create a string using any of the symbols from the alphabet sigma. Language over sigma is very similar. It means that each string in L is created using symbols from sigma. Okay, so in other words, it means that, right? So in other words, equivalently, it means that for every W in L, W is in sigma star. That's what it means. Okay. Right? It means it's in each string in the language is over the alphabet sigma, right? So, or in other words, each string in L can be is created using symbols only from your alphabet sigma. Okay, so that's essentially what it means, what over sigma means in both strings and also languages. So it's an equivalent definition for languages. Right? Does that make more sense? Or okay, no, it doesn't. Let me think of a way of explaining this differently. Because remember, what is a language, right? A language L is just a bunch of strings, W1, W2, W3, and so on. It could be finite or infinite. And if you say the language is over an alphabet, then that means that each of these strings in your language, each of these are over sigma. So meaning that, yeah, exactly, yeah. The language which contains all strings made over sigma. So yeah, so I think that's clear. I think it's, then the first part, not all strings. What did I say? I said, oh no, yeah. So it means that your language has strings that are over the alphabet, sigma. We have, if you have this, you mean? And the second part, sigma, is something else. Wait, give me a second. I'm trying to understand your question. You have sigma equal lambda. I don't, what do you mean by the second sigma?
Hi.
Yep. Hi.
So, is it true that the language which contains all the strings, the language, sorry,
Yeah, no worries.
so we have sigma.
Yeah.
All the strings made over the sigma is language. Is that correct?
So sigma is the alphabet, right? Let's say AB.
Mm-hmm.
Sigma star
Yeah.
is all of the possible strings
Mm-hmm.
over the alphabet AB, right? So
Yeah.
you have strings of length 0, that's lambda. You have strings of length 1, of length 2, and so on.
Yes.
Right? And so then a language is a set of strings, where each of these strings are in here. Right? So the first string could be A, the second string could be AA, the third string could be, A cubed. And so when we say L is over, the language is over the alphabet, it means that each of the strings in the language, right? Each of the strings in the language, are you with me or no?
Yeah.
Okay, each of the strings in the language can be composed, so they're a sequence of only symbols in your alphabet. Okay?
Okay, I understood until the sigma star. Okay.
Yeah.
And L contains W1, W2, W3, but what is W here?
So W is a string.
Okay.
String,
Just
let's
one
say
string.
let's say it's the first string of your language.
Okay.
So if you say that L is over sigma, then that means that each of the strings in your language, so suppose you take the first string, the first string is going to be composed of a sequence, so let's say A, a sequence of symbols over your alphabet. So this is a sequence of symbols, right? And each of these symbols are in your alphabet, right? So all of the strings in your language are sequences of symbols in this alphabet.
Oh, okay. So you're saying that L doesn't need to contain all the sigma star.
Yeah.
Doesn't.
An equivalent definition for a language is that it's a subset of sigma star.
Okay. Okay.
Does that make more sense?
Yes.
Okay, very good.
Thank you.
No problem. All right. I think there was another question. Question A, shouldn't we? Oh, this is the question I didn't answer. Let me answer Shijun's question. So shouldn't we delete A, B, since it is a useless production? Give me a second. Yeah, I'm thinking that you're right. Yeah, you're right. Yeah.
Actually, I think because the lambda's there,
Well,
A can go to lambda. So when you do the first step, that becomes just BB, a B capital B.
yeah, no, but because like when you remove lambda productions, remember what happens? You get BAB, and then you also get BB, right? But
Okay,
this guy is useless. Yeah, that's true. Yeah.
I don't think so because you can.
Because if you start at A, imagine.
Like for example, if you wanted a series of small b's,
Yeah.
and then
Yeah, no,
you
you're right.
end with only a single one.
Yeah, that's true. Yeah, so because you could do like BAB and then B, BB, B, and then yeah, like you can actually lose the A basically, so it's not useless. Yeah, you're right. So
I think it's only useless if there's no other possibilities for A to go to.
Yeah, that's right. Yeah, that's right. Yeah, so this isn't useless. So it is generating. It is generating because I can replace A. I can replace A with let's say what you just said with BB and then B, and then I can replace these B's with a bunch of B's. So I can generate using this production rule. So it is not useless. Yeah, good question though. Yeah, I mean, it's normal that it's natural that people have questions about the question I didn't go through, but yeah, I mean, I went through the solution twice, so I think it should be good. Yeah, so useless, the production is useless if either it is non-generating or it is unreachable. But in this case, I can reach A, and it does generate a string, right? It allows you to generate a string. So it isn't useless. Yeah, if it's, yeah. So Sarah, so it doesn't loop forever because so the first production rule I used was BAB. Then I took A and then I said, okay, I'm just going to use this to replace it here. And then I kept the B the same. and then I stopped here by replacing B with BB. So it doesn't loop forever, it terminates, it gives you a terminal string. And so it gives you a terminal string, or a sequence of terminal symbols. And so that means that it is generating. Okay, it's good point. Did I miss any question? I think someone had their hand up.
Yeah, I just have a quick question.
Yep.
I went back and tried to like understand question 7 again, the way like the wording.
Right.
The way I like rephrased it to make it more simple, it's basically asking, can we find a string V over AB such that the language is not CF? But from what I understood, what you did is you basically figured out a counterexample, right, to prove that it's false. But that would only work if you if the statement said for all V, right?
So I actually think we're saying the same thing, because you just said, can we find a V such that L is context free?
It's not a context free, because that's what the question is asking, right? It's saying true or false, can we find a V over AB?
But see, that's not, that's not an equivalent statement, because that would mean that your initial language is for all V. So because you're saying, okay, I'm going to pick a particular V to show that it's not V, to show that it's not context free, then that means that initially what's going on, how you're interpreting it is that you're saying it's for every V, not for some V. Because you're asking, can we pick right? So how do you show that something is not true if it's for all? You pick a particular V such that it's not true, right?
Yeah, exactly.
So, but that's not what we're doing, right? Because we're doing for some V, we're not doing for all V.
Right.
So that's why your explanation and your interpretation works if it's for every V in AB star, but not if it's for some V, right? Because let's say you pick one, but let's say someone else picks a different one, then if you can find at least one that makes it true, then it's true, right? Because it's kind of like, so maybe think of it this way. It's kind of like you picked one for it to be false, and then maybe someone else picked one for it to be true, but then you have a bunch of ors, right? So false or whatever, or true gives you true. So that's another way that I think you could see it.
Oh, okay, that makes sense.
Yeah.
Right. I think I got it. Okay.
Okay. Sure. Yeah, so that's a good point, Ronaldo. Best way to find if it terminates is if it has, to look at the production rules that have terminal variables only. That's a good trick. I agree. That's what I was doing. Like you try to see, can I make this terminal? Can I make this terminal? And then you say, oh yeah, well I can if I go through an extra step. Yeah, I agree. Very good. So again, any questions that you have? Yes. If lambda belongs to L, then what is different in L star? There's a lot different. If lambda belongs to L, L star is L0 union L1. So far it's the same, union L2. So it has every possible concatenation of L with itself. So it has, remember L2, the definition is x such that x is an L, right? Well, this is the concatenation. So for example, L a n b n, n greater or equal to 0. This contains lambda, but then L star, I'm not going to do L star because that would be crazy, but L2 is a n b n, a m b m. for n, m greater or equal to 0. So very different, right? It's L star in general has more elements than L star has in general more elements in general than L. I mean, there are some cases where that's not true. Like for example, sigma star star, that's always sigma star, and lambda star, that's always lambda. So in this case, they have the same, but I feel like those are probably the most famous ones and the easiest ones to think of where it's the same. In general, it's not going to be the same. Another question, say lambda is one of the accepted in an NFA. No, it doesn't. So that's a good question because so your Alex, your question would be yes if it was a DFA. So for a DFA, the only way for lambda to accept the only way for DFA to accept lambda is if you start like this. Right? There's no other way because in a DFA you're not allowed to have lambda transitions. However, in an NFA, you could have something like this, right? This is a valid NFA, and the initial state is not a final state, but it does accept lambda. So it doesn't necessarily mean that Q0 is one of the final states. Yeah, no problem. It's a good question. See, that's actually, those are very like good types of practice questions you can ask yourself. That, you know, I mean, it's easy to MCQ on that, right? So, so yeah. The tricky situational questions, yes. 335 is known for tricky situational questions. It's also known for making students, you know, you're essentially the goal of this, one of the goals of this class is try to become very good at MCQs, which it is what it is, right? Okay. So maybe I'll wait, because I mean, I'll wait, once there are no more questions, I'll wait another like 5 minutes. But if there are more questions, I mean, I can stay until, you know, whenever. Although the file for the video is going to get really long, but that's a me problem. So I think someone actually asked, when was I going to post these? I'm going to post them right after the tutorial ends. So yeah. For pumping lemma for CFL, why do we have to, okay, that's a good question. So let me actually, to answer that question, let me go to my pumping lemma tutorial. Is it 11? Yeah. Okay, so no one freak out. This is a different tutorial. It's just to give you the definition. So why do we have to consider all cases? Because of how the pumping lemma. Yeah, Stephen. So for pumping lemma for regular languages, so the pumping lemma for regular languages is different because what you say is that W is X, Y, Z, and XY is less than or equal to M. So that means that XY are within the first M symbols. So if you pick a string W, so let's say you have a string W, the fact that you're decomposing W as XY means that you're always going to start here, right? So you don't need to look at when XY is here, because you know that your decomposition starts with XY, right? That's different for the pumping lemma for context-free languages, because what it says is it says that, you know, you have this decomposition. It just says that this has to be less than or equal to M. So meaning that if you pick a string, maybe you have u, v, x, y, z. So z is here, v, x, y is here, and u is here. Maybe this is within m. Okay, so imagine this is like a, m, b, m square. So it could be within the m's, right? Sorry, it could be within the a's, your vxy, but then vxy could also be within your b's, okay? And it could also be in between. It could be v is an a and y is an b. So you need to consider all the possible decompositions, because if you just say, so an incorrect, let's say an incorrect, you could say AM, BM, right? Let's say MBM. We know that this is context free. If you said, okay, I'm just going to say VXY is within A's, and I'm going to pump up, so I get A, M plus K, BM, then you would erroneously say, okay, I have a contradiction, I'm done. But clearly you're not done, right? Because you haven't considered when VXY is here. And most importantly, you haven't considered when VXY is here, which at that point, you're going to see that you don't get a contradiction, which leads you to believe, it doesn't mean, but it leads you to believe that this is context free. So, I mean, basically, like the summary of my spiel there is you need to consider all the possible cases, because if you don't, you can come to the incorrect conclusion that something is not context free when it is, which would be bad, because then you would be wasting more resources than you need to accept something that can be done more easily, basically. But mathematically speaking, the reason why you need to consider cases is because now what you're pumping up is between two strings. So it's between two strings in the formulation of the pumping lemma. And so this can be anywhere, basically. So that's why you need to consider all the possible cases. So I hope that's clear. Is it always 5 cases? No. So it doesn't necessarily need to be 5 cases. I have an example here where, how many cases are there? So here there's 5. Here there's, 7. If for example you have an square, then you actually just need one case. You could just, right? You could just have the case where, well, you only have the case where VXY is within the A's, and then if you pump up or down for, in this case, for for just once, then you'll get a contradiction. So, but that's the only case. That's the only case because you only have one symbol, right? You only have a sequence of a single symbols. So when you scan VXY, you only have VXYs within the A's. But as soon as you have B's, then you're already gonna have at least 3 cases, right? You're gonna have VXY is here, VXY is here, and VXY is here. You might have more cases, right? It depends on how you're arguing, but you're at least going to have 3 for sure, and most likely more. Okay. And if we add C, well, if you add C, you at least have 5 cases, yeah. So if you have C, you could have this case here, this case here, and then you could probably, mess around and get more cases, but you at least need 5. That's for sure, yeah. And the same argument, you need 7 for if you add a D and things like that. Yeah, so as Ronaldo is saying, it depends on, what the sequence looks like. So if you just have one symbol, then you're going to have less cases. But it also depends on how your language, what your language is defined as. So Sarah, what are some problems or topics you consider adding? Oh, that's a good question. So give me a second. So I was gonna add more like I wanted to add more like property languages, like for instance, I don't know, like just it. So let me go back to the review slides. So if I could have, I would have added more things like, you know, properties of languages, like if L complement is finite, does that mean that L is always infinite? You know, something like that. I mean, there's a lot of questions I wanted to add, to be honest. But, you know, we would have been here until 10. So, ambiguity, yeah, I didn't even think of that, but that's a good topic of questioning. Like, also, like, if you have an expression, like you have a regular expression, you have one, and you want to check if it's equivalent to another regular expression. So I had intended on adding those, but I cut them out. And then I would have added more questions about grammars, like if you're given a grammar G, which is regular, like what's the length? What's the minimum length of strings in L of G, so something like that. You know, like, but a lot of things you can do with regular languages, like you could regular grammars, you know, how many strings of length 5, or how many strings of length less than or equal to 5, or you know, I mean, you can think of, there's a bunch of but if you get one, like if you know how to do a certain type, then you can know how to do kind of the rest. But yeah, that's what I would have wanted to do. I want to ask more closure property questions, like for example, if you have L1 is a subset of L2 is a subset of L3, and then let's say L2 is regular, then what can you say about L1 and L3 if, let's say, L1 is finite, or if L3 is finite, or if L1 is context free? If L1 is context free, what can you say about L3? So because, you know, I think I already did all of them for like for the midterm review. I did all of the possible closure properties I could think of for 2, like for binary closure properties. But now if you add an extra language, then it gets a bit funky. So things like that. Yeah, so so that was from maybe before the midterm, what I would ask. So I also gave you an example of what I would have said for like, for GNF and CNF, like if G is both in GNF and CNF, then what does that mean? If this is true, then is G regular, right? And then we saw that actually, yeah, it does mean it's regular, because it would mean that you only have terminal symbols, right? So that, also more questions about tracing PDAs, both Dpdas and regular PDAs. I mean, these are all questions that you can also find in just my regular tutorials. Like they're more in depth, right, for each topic, naturally. You know, like, yeah, I think for Dpdas, I kind of asked all that I wanted to ask. Just maybe like closure properties for DCFL and CFL. Those are very good. Like, I know there's a question in your worksheet, like if it's DCFL and you intersect it with a regular language, then you know what is that? Yeah, yeah. So those are subsets. Where did I put that? Wait, did I go up or down? What the heck? Yeah. So these are subsets, and then based on what this is, maybe you can conclude what this is, or based on what these two things are, can you conclude what this is, and sort of combinations like that. Yeah, so as Alex, the question from Alex, if L star is regular, that question actually is also in the midterm review. And I think I even solved it because I thought it was a very nice question. So yeah. Yeah, so tracing PDAs. What else would I want to, what else did I want to ask? So you mean this? Like the subsets thingy? So we would have, so cool. Yeah, so I don't know, I'm just making up an example off the spot, but like if you said that L1 was context free and L2 was regular, and L1 was a subset of L2, well, that doesn't actually necessarily tell you that L3 has to be context free. L3 could be regular or context free. So it wouldn't, because for example, you could have L of A star B star, and then you could have AN BN. So this is a subset, but then you could have sigma star. So that would be regular. Oh, also actually questions like you have regular languages and context-free languages. We didn't look at any options where it said like L is context-free, but not regular, because I mean these are very more powerful statements than just L is context-free. So just be careful when you're reading L is context-free. If you say L is context-free, then it means that it can also be regular. So that's a trick there. But if it says L is context-free but not regular, then you know that you have to be dealing with something like AN BN, right? Yeah. So tracing PDAs. Yeah, more closure properties on DCFLs and regular languages and things like that. Where am I? Yeah. And yeah. Yeah, so L, yeah, that's true. L is regular, but not, well, I mean, this is just saying that you're within, like, that means that you're just in here. So, I mean, it's plausible that that might be an answer to something, but typically it's more like L is regular. Because, I mean, oh, well, I mean, if L is regular, then of course it's context free, right? I mean, this doesn't make any sense. Yeah. Oh, at least 5 quizzes. Okay. Yeah, no, that's nonsense. L is regular but not context free is, I mean, it's impossible, right? If you have a set, if you have set A and you have set B and you say X within A but not B, then I mean this is just the empty set, right? There's no, it's pas possible. It's not possible, right? So yeah. So those are good to ask. And yeah, so as I was saying, like context-free, deterministic context-free, And also like recursively enumerable and recursive languages, if you intersect these with context-free, or if you do a union with context-free or with regular, things like that. That's useful to know. Pumping lemma stuff. Yeah, ambiguity is a section I completely skipped, but that's also important. So what does it mean to be ambiguous? What does it mean for, yeah, so like different derivations, you know, you can have different derivations, leftmost derivations or rightmost derivations for the same string. So you have ambiguous. So that's a very good question. What's the difference between recursive and recursively enumerable? Basically, L is recursive if there is a Turing machine M such that, so imagine you have M such that if you feed W into M, then it's either going to answer yes or no for every W, meaning that it's always going to halt, right? It's always going to halt on every input, okay? That's not the same as L is recursively enumerable. If L is recursively enumerable, the only thing you can guarantee is that if you have a W in L, so if W is in L, then M is going to say yes. So M is, so M answers yes. But if W is not in L, then there is no guarantee. There is no guarantee that, give me a second. There is no guarantee that M is going to say no, because there is no guarantee that it halts. Okay. So countability, so that's the countability is so that's also from 232. A set, just a set in general, is countable if you can enumerate, if there's a procedure to enumerate elements in your set. So for example, let me give you an example. Yeah, so if you have the set of, non-negative odd numbers, then this set is countable, because you can essentially, what you can do is, if this is your set, let's say S, what you need to do is you need to take each element in your set S and map it to an element in the set of natural numbers. So if you start at 1, you could say 1 goes to 1, and then, so let me write this out. So you can say 1, 3, 5, 7, so on. So 1 goes to 1, 3 goes to 2, let's say, 5 goes to 3, and so on. So you can enumerate all of the possible elements in S. So S is countable. And so the relation, give me a second before I say something that's false. The relation, because there's a direct relationship between so L is recursively enumerable if there exists a enumeration procedure. So this is an enumeration procedure for all elements in L. So that's an equivalent sort of statement, is that elements in L can be enumerated. Or in other words, you can count, you can essentially, there's an enumeration like this that allows you to map for every element in L, an element in the natural numbers. So that was covered in lecture also, I believe, when they were trying to show you that there are languages that are recursively enumerable, but that aren't recursive. So, okay, decidability is slightly different because we don't really say that a language is decidable. We say that a problem, and actually a decision problem. So a decision problem is just a problem where the answer is yes or no. A decision problem is decidable if there is a Turing machine that for each instance of that problem can say either yes or no, right? So it doesn't really, it's not like it's a, like now you're dealing with problems. So you kind of just need, you need to be a bit more careful because you need to say that, okay, actually problems can be mapped to a language, and then that language is recursive or something. So, but recursive and decidable are different because recursive applies to languages, decidable applies to decision problems in particular. So the halting problem, for example, is not decidable because you know, what does the halting problem say? It says that you're given a Turing machine M and an input W. Does M halt on W? And so this is undecidable because we have no algorithm that tells us given an arbitrary instance, is this true or is this yes or is this no? Okay. So that's a halting problem, and that's decidability and recursiveness. Yeah. So essentially, if a problem can be solved by a yes, yeah. If, well, I don't know what you mean by recursive Turing machine. I don't think that's a proper qualifier for a Turing machine. But if the Turing machine can halt for every possible instance of the problem, so in other words, say yes or no, then it's decidable. Okay, yeah. Turing machine that never enters, yes. So in other words, the Turing machine that never halts, yes. Because if it never halts, that means that if the Turing machine never halts, then that means it's either going to give you yes or no. It can't give you anything else, right? No, so calculating pi is decidable. That's actually a very interesting question. Calculating pi is decidable because, well, actually, first of all, the problem of calculating pi is not a decision problem. So you can only say a problem is decidable or not if you can only say a problem is decidable or not if it's a decision problem. Okay, so calculating pi, you know, that's you're not formulating that as a decision problem. If you said, for instance, is there an algorithm that calculates pi? That problem, that decision problem, is decidable because you can answer yes to that, because there is an algorithm that does calculate pi to, you know, an arbitrary number of precision. Okay, yeah. So what kind of questions can we expect for decidability? So you need to understand the definition of what a decidable decision problem is. Also, what's another? So for the very last part, they're not gonna ask you something about, like, you know, reducing a halting problem to something else. So that's like super complicated, and that's something that you haven't seen in lecture. So it's not going to be something like that. It's going to be something more like, you know, well, I mean, don't take my word for it, right? But it seems as though it might be more like high level questions, like, you know, but you need to understand what the halting problem is. Why is there a contradiction somewhere? What does it mean that it's not decidable? So really understand the definitions and understand what they're saying. But you know, it's very difficult to formulate a question that's doable for something like decidability, because decidability is a very difficult topic. Like, you know, it's a constant area of research in computer science. So no, don't be scared for decidability and halting problems. Like I don't. So from my experience, it's theory intensive, which is more of a, yeah, well, I don't know. It actually, you might be surprised. It's pretty, like they could ask you, like basic questions about decidability, but then, worded trickily, and then that can become an MCQ. So if you really understand what, like the basis of it, then I think you should be, okay, right? I mean, I haven't seen the final, so, don't go back to your professor and be like, oh, the TA screwed me over. Just like, but I don't think, like, if we're thinking reasonably, it's not going to be something extremely difficult for that, right? No, so I don't. TAs don't know anything, so that's the lesson you should take away from this, is that TAs know nothing about the workings of, like, we don't even know what the answers to the assignments are until we get the solutions. So we get the solution at the same time as you. We get the quiz answers at the same time as you. We get the midterm like answers at the same time as you. So yeah. No, that's fine. Yeah, that's cool. I don't mind. If you have any more questions. Actually, maybe I should just stop. Like, maybe I should record again. Just okay, I'm gonna stop recording and then just leave the rest of the recording for just Q&A. Okay, so then maybe it's good that, okay, I'm gonna